Hey, 5 more minutes, we should go.
For heat and
Do you not like them? It's just like
Oh, is this timetable wrong?
Any job?
Have you already had it?
You just call them all.
We got to stop. We got to stop.
Different topic means
We went to get stuff.
Yeah.
same topic, just copy.
So we got to stop.
Having pre-conference is not paraphrase, just copy. Just on both will get 0.
Did you go to the live?
누나를 항상 응원하고
Yeah,
Not
yeah,
taking
yeah.
efforts.
뭔가 떨리는
Shit,
거
that's
그래. 듬직하다.
Separate because that topic is like separate.
I was laughing at the register for corrosion last week, where there was like loads of red marks and nobody came. It was the only lesson I Friday. No, did you see the register for corrosion? For last week, red register. I was thinking, why was everyone off? And I thought, hey, only one lesson on Friday, nobody came to work. You can always just turn up yourself. No, I'll do it, but don't start telling me to practice your CPT. You'll get what you get. You do it, finish in your last. And there's no last day. Did you not see my Arabic? When you wrote Arabic, what do you want me to do? Just trace.
It's like say 11 icon.
Okay, I'll practice. You do realize it's not
trying to get it so that we actually see the lecture
on the screen rather than half of it, which wouldn't be very good.
You get 5 or 10 minutes more, and then you get late to do the next
If you miss that, you miss 80%. Well, there's only 12 classes. Each percent is 2.5. You want to read the rush, like when it plays pretty good. Year 1, 2, yeah, each one's 2 hours, 12 days, 24, 48 hours, but it's 24, 12 days, 2 hours. So all it takes is 3 classes and 6 lessons. Or is it in, is it for both? Because no, but they've only take a register, so it must be just it's got registers, so if you miss 3, it can't be the other guys. Did it? I love how I've not received one email. And you're more likely to get is that what it is? You need to verify that. So you see the medical now? Yeah, it don't work like that, do it. So it's got a added that one. You need a medical, it costs £60, but it's like £5 medical. So I had to take the classes and say, but it was that's the only time I got basically got 0. No, just basically a doctor's signature. I just took consultation. I was ill then, but I was like 99%. I would not be I was really negative. I just had my vaccination. I just went out. I don't know what it was. It just went really hard to score 100%. Especially in my school, which is over 100 still. So one mistake like is even worse. I literally in a tennis club, if you do one mistake, it's 99. They normally prolonged it to 10. But in a 100 club, they just leave it like 99. I was getting time vaccination. Whatever it was.
I'm struggling. what I'll try and do is sort of get through it with this thing, and I'll sort this out. But by the time I phone the AV people now, they won't come and fix it. I want to try and get a few things said today, at least. So we talked in the previous lecture about making pipelines, and the last thing that you want to do is pressure test them. Now you don't pressure test the whole pipeline, you pressure test them in segments, and they usually pressure test when they're in the trench, when most of the pipe has been backfilled, and there are a few overlaps because you have to weld on end caps to maintain the pressure inside the pipe, and then those when the pressure testing's been done, those will be cut and joined to make a single pipeline afterwards. So it's an on-site activity, but the pumping activity for the water that does the pressure testing could be miles away from where you actually measure the pressure. Now if you have a stress-strain curve, this is a stress-strain curve here, although it's cut off at the edge, you'll see the elastic part, and then we go into the plastic part. There are different codes, different design codes, which have different pressure points for which to do the pressure test. And different companies use different values of that. This is the basic one here, which is the design pressure divided by the safety factor for that particular situation. Has to be well less than the yield stress, and it's usually about half of the ultimate strength of these materials. Sometimes you multiply that by a factor, and that puts you up to this point here, and that's a test protocol according to this DBGW standard. And then there are other standards as well which allow you to pressure test above the yield stress, so that you look at overload conditions. So because these pipes are designed to be used well below the yield stress, if you pressure test above the yield stress, you know you're going to have gone higher than the maximum pressure that everybody's likely to include. And there are a whole set of different tests as to where you go on that. And they're based upon a certain amount of plastic strain being introduced. The idea is that if you've got a distribution of defects in the pipe and in the welds, the higher you put the pressure, the bigger and bigger the defects are that actually run and cause failure. So at the low pressures, you're looking at enormous defects, and as you get up to higher pressures, the defects that will cause failure get smaller and smaller until it's got to a stage where you think that's not a critical size. So which is the best one to use? Well, if your design pressure and operating pressures are down at here somewhere, which of these things you use doesn't really matter too much. But there are other considerations like bending and seismic movements and things like that which you take into consideration. And so, as I say, companies have different standards for doing this. So the benefit of a high-level strength test is effectively it takes out all the big defects, because if you fail that pressure test, you have to go and repair it, and then you've repaired it usually with good defect-free welds, so you're not going to get any problems. And so operational failures, which occur later, tend to be much, much less likely. So if you put a high enough pressure test in, that's okay. So basically, if the pipeline contains defects above a certain size, then you're going to have a failure in the hydro test. And if you repair the system and get it work, you've screened out all of those big defects. And hopefully that means that if you do it at second test, the smaller defects that remain would require a higher pressure to fail. And this graph, if you could see all of it, shows the pressure of failure against defect size, and you can see as the defects get bigger, the pressure is smaller that you need. And so P0 would be the operating pressure that you wanted to run at, and PT would be the test pressure. If you run at the test pressure, these small defects will actually fail, and anything bigger than that would actually fail. So hopefully you've got a set of defects in your operating conditions which are much smaller than the defects will be required to cause failure under those conditions if you do the hybrid test correctly. You have to think about different activities when you look at road, rail, river crossings. So this is a road crossing here. You can't usually dig up a road and leave it out of commission for months while you do a pipeline. So normally you put a tunnel underneath. And the pipe segment is inserted in the tunnel and everything's done properly. And then the ends just sit there waiting for the pipeline to catch up. And you can then have different types of clamps to hold it together. So this isn't an internal clamp, this is an external clamp that can be used to hold parts together, and you weld in the gaps. You can't quite see it in here, unfortunately, on this picture, but you need different equipment for dealing with these tie-ins. That's the point that I'm trying to make. Because you can't rely on an internal clamp being pulled all the way through as you do with the normal manufacture. Probably wouldn't be able to get it into some of these tie-ins because sometimes there are bends that you have to put in that are quite sharp to make sure you match up the pipe to the crossing, and the crossings don't necessarily go perpendicular to the pipe. They can go at some strange angle, and it can be very difficult to sort things out. So sometimes you're putting tie-ins into a pipe and you're actually running gas through the pipe. So you may have a situation where in order to maintain productivity you have to connect a spur onto a pipe, and that tie-in may be done with the pipe actually filled with gas. And that's a different set of processes completely. So by hot tying, I don't mean to say it's hot while the guys are working there. That means that the pipe is live. And if you do anything to cut through the pipe or let gas out, when you've got flames around from preheating torches and things like that, the whole thing can go bang. So you have to have a very, very careful team that are knowing their procedures very well to ensure that happens safely. In Canada and in Alaska, we can't trench because the ground is frozen solid and the permafrost is just too difficult to dig through. So pipes are above ground mostly, and they have to have protection from extreme cold and extreme warm temperatures. So the pipe supports and the externals to the pipe have coolers, and they have sometimes trace heaters to maintain the pipe in a stable temperature situation. Cooling is usually more necessary because the product flow through the pipe actually leads to some heating of the material. And so you sometimes have to deal with that heat, particularly in hot places. And the fact that you've got a good solar gain heating of the material if it's sitting above the ground. So it's the temperature changes which is the problem. It's not so much that the pipeline's at a high temperature or a low temperature, but it might be at a high temperature in the day and a low temperature at night, and you have to have heating cooling systems that try and minimise that variation. So there's extra facilities necessary for doing that. We don't in the UK tend to worry, we just dig everything in a hole. And things like about the underground temperatures, it's fairly constant, about 5 degrees, I think, in most cases, it sits there. So it's not something that I can tell you much about, but I know it happens. Double jointing, productivity. If you can actually take two pipe segments and join them in a factory, this says submerged arc welding of the pipe, so this is a submerged arc welding place. So we're doing a girth weld by submerged arc welding in a factory, and we are delivering 24 metre lengths of pipe rather than 12 metre, or 36 metre rather than 18, or 36 metres rather than 12 metres because you've done a triple joint, which you can happen. And now, if you are able to deliver that long section of pipe to site, and if it's flat enough, and if there's lots of ifs there, then you can do that. These types of processes are much more common in offshore manufacture because productivity is so much more critical in those cases. But you imagine if you've got a complete pipe length which is 3 times as long, then you've got 3 times the productivity when you're on site because you can do the same number of welds per day, and some of them have already been done. So in order to have this submerged arc welding process working, the pipe sits on rollers. I don't know if you can see them here. So the submerged arc welding kit is fixed, and then the pipe just rotates so that you can make the full girth weld. And that's only really feasible because of the nice simple cylindrical geometry. Okay, so that's the onshore pipe construction. What I want to go on to talk a bit about is the welding processes that are needed in a bit more detail. Now we're losing about an inch off the side of the slide. I'm sorry, I'll read what I can for that, but it's the best I can do at the moment. We have lots of different welds to make a pipeline. Lots and lots of different welds. So you've got our longitudinal welds in our UOE pipe, let's say. We've got the girth welds. We've talked a bit about those. You've got a hot tap, so you've got welds holding this split T in place. You've got welds holding elbows and joints in place. For some of the smaller tapped pipes, you might have a different set of welding processes, like flash butt welding, for instance. You might have perfect welds, and every now and again you've had to do a repair, so there's a repair weld. And when we go out to pig traps and things like that, we have things that are coming out of the ground which have more variation in temperature, and you may want to be a bit more careful about your welding procedures, so you might have some low hydrogen welds. Then you've got to put cathodic protection attachments on, and those might be brazed, they might be welded. And then there's a welderlet in here. We talked about welderlets in the fittings because we want to get an access port into this pig trap. These are mainly shop fabricated welds here. These ones are, but these ones are site fabricated. So there's a mixture of welds and a mixture of processes as well. So we've got shielded metal arc welding, which is stick welding, manual metal arc welding, different terminology depending on which country that you come to. You've got gas shielded metal arc welding, MIG welding in this country, metal inert gas. And you've got electrical resistance welding, ERW, submerged arc welding, and different shielded metal arc welding processes might happen. And then you get some weird welding technologies when you look at the small lines that come off the main weld. So flash butt welding and explosive welding can be used for putting flanges on, for instance. All I want to say is that welding isn't just one process with one set of procedures. It depends on what you're trying to do. So there'll be different procedures for each of these different types of weld. And they're not always comparable, let alone the same. So over the years, a number of different processes have been used. Onshore pipeline welding initially started with simple oxyacetylene torches. Acetylene has got the highest energy content of all the gases that are available, so we can get the highest heating of a material from an oxyacetylene torch compared to any other gas that you use in conjunction with oxygen. But you still can't really heat thick metal up. It's only suitable for rather thin metal systems. So nowadays oxyacetylene is used largely for preheating in the industry rather than for actually welding. Manual shielded metal arc welding, manual metal arc welding, stick welding, that is the common on-site welding technology. It can be mechanised. but not easily. But there are mechanised gas metal arc welding, so that's gas shielded metal arc welding or MIG welding in this country, where you have a gas cylinder that you have to take with you that provides the protection. The manual systems, the stick welding, it's the coating on the stick that provides the protection of the weld. So you don't have to carry a gas bottle with you. Sticks are relatively short, so long. So when you've welded that material, you've got to eject it and get a new stick. So those welds have start-stops in them, and that's not so good. So flux cord arc welding was designed to have some of the benefits of the mechanised gas system without having to have a gas supply. So you have a tube of weld metal and you put the flux that provides the protection on the inside of a tube, and then you can wrap that up and you can feed it like a wire into the process. And then flash butt welding is sort of variant on resistance welding in the sense that you get a large current between two surfaces and sparks going between them that heat them up, and then just press them together to make a joint in a one-shot process. Okay for smaller pipes, not good for big ones. So you get the actual pipeline welding, and then the collections. Mainly we use the same processes, but you can have brazing, thermite welding, and all sorts of other processes if you really want to. Largely for the cathodic protection connections onto the outside of the pipe. And there are stud systems that you just put them on and pull the button, and you get a spark, and then this thing goes on the surface. It's almost like a local resistance weld, and then some of them are thermite, so that's aluminium using aluminium metal reducing iron oxide to form iron in the reaction zone. So you're making steel in situ, effectively. And then brazing is like a cast metal in the gap between the two parts you're joining. Right. I'll try and read some of the stuff that's off here just so that you've got an idea. These are a few definition terms just so that I'll say things and then you know what they are. You can come back and see them on the PowerPoint files, which are on Blackboard, as I said. So manual welding, everything is done by hand. The electrode manipulation, the feed of the weld metal, it's all done by hand. And that generally is what you would see on site, but it's not completely manual. There's a lot of use of semi-automatic welding. So in a semi-automatic weld, the electrode tends to be fed mechanically, so the wire is fed mechanically to a welding gun, but the gun manipulation is done by hand. So part of the skill is reduced by that process. Mechanised welding generally has the electrode fed mechanically into the welding gun, and the gun is fixed to a carriage which then orbits the pipe on a rail or a guidance system. And it should be completely automatic, except that there are problems with alignment and there are problems with individual things happening on site which aren't covered. So usually there's an operator that supervises this process and can adjust it. So it's not totally automated. Mechanised welding is mechanical welding, but with an operator to make sure it's being done well. Fully automatic welding, as its name implies, should be set up and totally controlled by the machine, and no operator supervision is required. And you can buy orbital welding systems for small pipes that work exactly like that. They tend to be great because you're doing a repetitive job in a factory lots and lots and lots of times for making short pipe runs or for making the water supply loops for processes and things like that. They're great because they're welding things that are this sort of size. As soon as you go this big, they don't work anymore very easily. And again, they're not easy to do on site, so they tend not to be used. Now, most welds in most pipelines are not a single weld pass. They might be 6, 7, 8 weld passes, and that takes time. So there's always been use in the industry of what are called one-shot welding processes. So you set things up, you run the process once, and the joint is complete. And that is totally automated, because all you have to do is set things up correctly and then press the button, and then everything should happen. Explosive welding is like that, flash butt welding is like that. There are some friction welding examples that are used in the industry, particularly for downhole tubulars and things like that. Do they get used in gas pipeline construction? Not really, only in the tie-ins, and rarely. Electron beam welding has been looked at by some of the big oil companies for 20 years, and although it's theoretically possible to do, it hasn't actually made big market penetration because the cost is just too prohibitive. So people would like to have a one-shot weld, because productivity would go up of making your lines, but doing it in practice is a lot more difficult, so it tends not to happen. Again, some process abbreviations. I tend to use the UK abbreviations, and sometimes I have to think twice when I see the American definitions, which are up there. And again, it'll be easier to see this if you had the slides. I'm sorry about the problems in this lecture theatre. So shielded metal arc welding, known as manual metal arc welding or stick welding in the UK. The shield comes from the flux coating on the outside of the welding rod. Gas metal arc welding, which is known as MIG welding or metal inert gas welding, or metal active gas welding, or MAG welding, or carbon dioxide welding, or CO2 welding in the UK. There's lots of different names for what is essentially the same process. In this case, a shielding gas is provided around the arc region to stop oxidation that comes from a gas bottle. MIG stands for metal inert gas welding, and if that shielding gas is argon, that would be a MIG weld. MAG welding is an active gas, and usually those are the ones containing carbon dioxide, because if you weld steels in air, there's a chance you can decarburize the surface of the steel, you can leave some carbon loss from the weld. So if you put an active environment with carbon in it, it's less likely the carbon will come out of the steel. So MAG welding, metal active gas, or CO2 welding, is really designed for steel to keep the carbon content exactly what you want. Gas tungsten arc welding, or TIG welding in the UK, tungsten inert gas. This is the one where instead of having a wire fed through the gun, as you'll have in MIG welding, as your consumable, you just have a fixed heating gun with a tungsten point which does not melt. And then you have to have a separate feed for a filler. So tungsten inert gas, or TIG welding, is perhaps the most skilled of all of the welding processes because it's a two-hand process. It's also the highest quality welding process, and it's often used for things like ring passes, the first welded pass. It's also the highest skilled welder that you'll have on your team, and that means the highest paid welder in the team. And they know it. You know, if you're very good, if you've got the manual dexterity to handle a consumable and a torch and get good quality welds and do it day in, day out, hour after hour after hour, you know you can command a premium salary. So these are people that you have to look after in your organisation. Not everybody can do it. In the UK, you go to the Welding Institute, you can get a ticket for welding, a training for welding, that basically says you meet minimum standards for doing it. Any idiot, and that includes me, can get the MIG welding standard. You just have to be able to hold a torch and point it in approximately the right direction and you get everything that you need. Stick welding is a bit more complicated, but again, that's quite easy to do. So if you get 10 people getting the MIG welding one, you'll get 5 people getting the stick welding, and you'll get 1 person doing the TIG welding ticket at any one time, just because the levels of skill are there.
So stick welding is the same as
Manual metal arc, the first one. Yeah. The Americans call submerged arc welding submerged arc welding. That's something that's good. That's what's done in factories. That's what's done for making the pipe segments. That's the one with the granular flux on the surface. And we agree for once. They say the UK and America are two nations divided by the same language. Because we don't usually use the same words and the same descriptions for things. Electron beam welding, flash butt welding, and magnetically impelled arc butt welding. If you get an arc, it's a flow of current, put it in a magnetic field, you can force the arc to move in certain directions. So if you have a rotating magnetic field, you can make the arc go round and round in circles, and that means you can heat a larger area fairly uniformly in an automated fashion. So sometimes in butt welding, you put a magnetic system around the outside to distribute the arc heating evenly around the surfaces. Works great, except when you try and do it in the field, when it's a tricky thing. So again, some factory systems use this. I've not seen it used successfully in the field. Okay. Again, I'll have to read what's off the edge. Onshore pipeline welding, we think it should be easy, shouldn't we? I mean, welding's been known about for years. We've solved all the problems with welding. We know exactly what to do. And therefore, if we know exactly what to do, we should be able to automate it very easy, shouldn't we? I mean, we know what the problems are, we know what the targets are. There are many, many manufacturers of welding equipment. They should be able to come out with a solution every time. So what are the problems? Well, the problems are largely to do with not the welding process, but everything else. So when you actually set up a lot of welding processes, you weld down onto something with a weld pool, which you can look down onto. So the weld pool is held in place by the material around it. Now you're welding one of these pipe ends, you're welding downwards vertically. So you've got to worry about the effect of gravity. And whether you weld upwards from the bottom or downwards from the top makes a difference. What about fit up? If you put two pipes together, if they're nice and close and everything's perfectly spaced, yeah, welding is straightforward. What happens if the pipes are canted like this, or if the gap between the pipes is bigger? Then you've got problems in actually doing the welding. And you can't guarantee when you're manually handling these pipe segments that you can get perfect alignment every time. And every pipe is different because they're made in a batch process. They're not made to an absolute standard. They are made to pass a minimum standard, but there's no maximum to that standard. And site conditions vary. Everybody likes making pipelines in the summer when the sun is shining. Nobody likes making pipelines in the middle of the winter when there's a force 9 gale blowing, it's raining, the tent is blowing away, but you've still got a productivity target and I've got half a kilometre of pipe to do by the end of the day. People can adjust to those conditions, machines can't. And that's the reason why we still use people in all of these processes. So welding's not easy, but if it's done correctly and we have the right combination of people and automation, then we can get the best outputs. So here's a couple of examples. Again, I'm sorry about the thing being cut off here, but you can see a welder here with a blowpipe. So this is an oxyacetylene torch. So there's one hand with the torch, the other hand with the consumable. It's welding like this. Consumable's getting shorter all the time, and the torch, so he's going down and he's moving round. Quite a skilled procedure. So gas welding, which it was known as, was quite a skilled process. And the thing I really like about this is the guy's wearing a Homburg hat. You know, there's none of the safety things that we have nowadays. Elegance was the important thing. Yes. So another type of joint which get around that problem and get everything lined up is this so-called bell and spigot joint. So you open up one end of the pipe and you insert the other pipe in, and then you just weld around the edge with a fillet weld. That was a very popular joint because it didn't need so much setup and the welding quality wasn't as essential. You can see here, there's all these lumps and bumps. These are the starts. So this is one stick's worth of weld metal, and then there's another one there, and so on, all the way through. It was very tolerant of all of that behaviour. But you're buying, 6 inches of extra pipe for every pipe segment that you do, and if you add up the amount of extra metal you bought just by doing that, that's a hugely expensive process. And it's much more difficult to line up and get everything in. The welding might be quicker, but the processes were not very good. So because it was slow, people looked for a girth welding process that gave you a single, simple welding joint. And they'd love it to be a single pass, but it turned out to be a multi-pass joint. None of these had particularly good mechanical properties, so for low pressure lines they were fine. Water pipes. Sometimes people in the industry say, oh, that's water pipe material, or that's water pipe welding, and that's the way of saying, that's not very good, I'm looking down on you. So gas engineers look down on water engineers, usually. Whether they have any right to, that's another matter. And you have problems with those welds. So a very common defect in welds is lack of fusion. You can see that lack of fusion defect there. So what does lack of fusion mean? You put the two parts together, you make the weld, and the weld wanders too far away from one of the two parts, so you don't heat it. So it doesn't melt and it doesn't fuse with the weld pool. And it looks a bit like a crack, but it's really a processing defect. It's not a crack. It's not a sharp defect like a crack. But that has to be repaired because there will be a leak with that. And the other one is undercut. So here's a good weld. And then this welder had a wobbly. And the weld, instead of doing what you normally do, there's a manipulation of the weld, sort of like this, going down there. And then the welder's gone. Probably because they're bored. And what's happened is all the weld metal's been deposited on this side, and we get an undercut here. So this part of the weld is not filled up. And then the weld tends to improve a bit afterwards. I saw one welder yawn and got a lovely undercut from that, so you can tell exactly what happens there. So you don't tend to employ welders for their ability to do complex things. You employ them for their ability to do the same thing the same way again and again and again. I could never be a site welder because I would be so bored with the process after about 20 minutes that all my welds would be awful. Some guys can get into the groove of welding and they can weld for 24 hours straight if there's a big repair job, and every weld will be the same quality every time throughout. And they're good. If you get one of those, keep them because they're excellent. They tend to be very strange people, I have to say that. If you can have that level of concentration for that length of time, your mind doesn't work the way the rest of the world does. And a very strange sense of humour as well. So, I once came back to a site to find that one of the welders had been annoyed with one of his friends, so he'd welded some steel strips around the friend's car so it couldn't be removed. And we had to get the cutting torch out to actually get this car free. And we then discovered he'd araldited all the door locks as well in the car, so that was pretty much a write-off. So you knew after that you didn't get this guy annoyed. Okay, so the stick welding, shield metal arc welding, manual metal arc welding, call it what you wish, process came into the industry in the 1950s and it's still used today. And for on-site welding, this is what you want to do. So we call it stovepipe welding. And stovepipe welding basically is two welders, top of the pipe, one welds one side, one welds the other side, and you weld down and you meet at the bottom. But the one at the top starts a bit before the one on the other side, so that when he gets to the bottom, the other welder can be out of the way when he gets there. Because you don't want two welding torches coming and touching. That's definitely a disaster. So it's quite a skilled process still. You can see this guy here, he's got 2/3 of the way round. See that stick is still a little bit long. he's got to weld right underneath, and in the end he's welding underneath the pipe. So he may be almost on his back, certainly on his knees, actually finishing that thing off. So this is not an easy process to do, and if you're kneeling in the mud, it's not a clean process, it's not a pleasant process as well, so you need to be able to do that. It's a very fast process. We used initially welding rods covered with cellulose because that gave the good hydrocarbon gas that was protective of oxidation of the surface, which is what you wanted to do. It's a very fast process. You can make the wire bigger, put more current through, deposit more metal. A bit less safe, but you can do that. But it requires high skill, and you cannot do most welds in a single pass. Generally there is a root pass, a hot pass, some filling passes and some capping passes. Maybe as many as 10 passes before you actually have the whole thing complete. So as I said, cellulosic electrodes were originally used, but that led to hydrogen cracking. And so there was a whole set of work done on preheating of the pipes to prevent that, to allow the hydrogen time to escape. And it was largely the standard for onshore pipelines and remains pretty much so today. Because site welding is being done in a field in the middle of nowhere. Offshore pipelines, as we'll see later, is done on a lay barge where the conditions are much more controlled. So you can afford to use more different welding techniques than have been done here. So finally, I'll just give you the schematic of the shielded metal arc welding, manual metal arc welding process. So what you have is a gun, an electrode holder, which usually have a spring-loaded clip, and that spring-loaded clip can hold on to the consumable. And the reason it's spring-loaded is at the end, when you want to get rid of the end, you want to eject it. So you squeeze the clip and flick, and you can throw the used rod away because it's hot. You don't want to handle it with your hands and things like that. And then you can insert a new rod in. That's connected to the power supply, and the power supply then connects to the return electrode, which has to be clamped somewhere to the thing you're welding. So there has to be a return path. You then have to bring the torch, the rod, onto the surface, current flows, and then you withdraw it a short distance from the surface, and then that current flow, which is just by conduction, turns into an electric arc between the end of the rod and the surface. If you're good at it, you can do that first time every time. If you're not good at it, and that includes me definitely, you have to touch it loads and loads of times, and you end up with arc marks all over the place as you try to get this thing going. There's a skill to be able to do it, to know exactly what you need to do. So what happens is the arc, we get electrons flowing in this direction, that heats the parent metal. We get ions flowing in this direction, that heats the consumable, which is a smaller volume. And the electron current's higher, so that's why we do it that way around. The end of the electrode melts, and it can drop under gravity, or it can spray, depending on the conditions that you choose if you're doing things above. And then you get some melting and degradation of this flux coating around the outside, and that creates gas, and the gas flows around the surface. It stabilises the arc because it's always in that gas, and it keeps the oxygen out from oxidising the surface. The weld pool is here. Notice the weld pool is pushed down because of the force of the expanding gases, and then it solidifies as the torch moves in this direction. Solidified metal is there. What the flux also does is it allows some elements to be added, like calcium oxide, which can react with iron oxide, form a low melting point layer which floats up to the surface of the weld metal, and that helps to protect things, and it creates what's called a slag layer. So you get this slag layer on the top, and that protects the cooling weld metal from further oxidation, but you have to clean it off because it's a brittle ceramic, and if you don't clean it off, the weld will be very, very weak. So you often wire brush these welds after they've been made to remove this, maybe chip it off with a hammer. Now, arc is current. You've got a return line here. When current flows through the parent metal, you get a magnetic field. Depending on where you put that return line, the magnetic field can push the arc around all over the place. And so the skill is, in this setting this up for pipes, is putting the return electrode in the right position. So generally you try to weld away from the return electrode. That way you have less problems. So these are all sort of things you have to think about when you're doing it on site. But it's portable. The power supply can be connected to a small generator, and that's pretty much all you need apart from properly looked after welding sticks. And that is a big problem on site, because if you want to keep water away and hydrogen embrittlement problems, you want to keep the electrodes dry. And if you're in a force 9 gale, as I say, in a field in the middle of nowhere, how do you keep your electrodes dry? So often they're sold in vacuum packs. And then some standards say you have to have a little oven. And you put the sticks in the oven and bake them while you're using them, and then just take them out when you need it. So you can have a little stick heater with pots you put things in. So that's extra equipment you have to have on site. So you're starting off now with a small truck for welding, with a generator and the welding power supply and the umbilical to that power supply, and all the ovens and heaters and the sticks and everything else, all the consumables. So this isn't now just a guy walking along the pipeline with a small power supply. This is a much more complex system. And as we get more automated, the size of this ancillary equipment goes up. That's why we need a nice wide right of way. Because not only have you got the cranes and things to go past, but you've got to get all these other things around them to deliver the gas or whatever to the welding stations. And next week I shall tell you a little bit more about that, hopefully when you can see all of the slides.
Almost after I've gone to chocolate. Yeah.